Welcome back. We're talking about Newton's method. We've talked about two different ways to interpret it. Now we're going to get right into talking about the specifics of the algorithm and also giving the main results for convergence. Newton's method has two phases, the damped phase and the undamped phase. So phase one updates as xt plus 1. I guess I should write everywhere inside here we're minimizing a convex function f that has a Hessian, so I can find its second derivatives. Phase one is xt plus 1 equals xt minus a step size that'll be less than 1 times the key Newton direction, which is the inverse Hessian of f times the gradient of f of xt. So as we'll see, the algorithm runs several iterations of phase one until it gets into phase two. And in phase two, it runs undamped Newton. Xt plus 1 is equal to xt minus Hessian inverse times the gradient of f of xt. And it's in this phase where we're going to have quadratic convergence. We need to talk about how we know when we're transitioning from phase one to phase two, and also how to choose the step size. For picking the step size, we're going to talk about an important algorithm that is also often used in gradient descent. In our discussions of gradient descent so far in this course, we've been talking about picking either a fixed step size that depends on the error we want, or a step size that depends on smoothness parameters, namely 1 over beta. For Newton, we're going to use something called backtracking line search. And it's the following. And of course, this only applies to the damped phase. Fix parameters alpha and beta then backtracking line search does the following. It basically keeps checking for this condition star, which I'm going to write. It keeps checking whether f of xt plus the Newton step it keeps checking whether this has improved by a specific amount, whether it's less than or equal to f of xt minus alpha times eta times gradient of f of xt transpose inverse Hessian times gradient of f of xt. What this should remind you of is the guarantee that we have for smooth functions that if we take a gradient step with step size 1 over smoothness, this is guaranteed to improve by some additive factor of the squared norm of the gradient of the function at that point. And if you look at what this is, if you look closely, you'll see that this is very similar to a squared norm of the gradient. In fact, if the Hessian were equal to the identity, this would exactly be the square of the Euclidean norm of the gradient. So it's very similar. The main point, however, is that we can always check whether this has been satisfied. So backtracking line search says, given this condition, start with step size eta equal 1. And check, does eta equal 1 satisfy this? If not, then we decrease eta by a factor of beta. Beta here is not the smoothness parameter that we've used previously, it's just some parameter less than 1. So this way we decrease eta, and so we're guaranteed that eventually this will be satisfied. So this is what's called backtracking line search. The main theorem says the following. The setting is that we have a function that's twice continuously differentiable. So we suppose that f is convex. I'm going to give it, I'm going to ask that it's little m strongly convex and capital M smooth. Remember that smoothness is a Lipschitz condition on the gradients. But now Newton's method also has a Hessian, so I need to put some conditions on the Hessian as well. So this is going to be a new condition. We haven't seen it so far. We're also going to ask that in addition to it being strongly convex and having Lipschitz gradients, we also needed to have Lipschitz Hessians. So this Hessian of f is L Lipschitz. Okay, so note that this is a new condition. We haven't seen it before. And what specifically does it mean for a Hessian to be Lipschitz? Well, it means that the Hessian evaluated at x minus the Hessian evaluated at y are somehow close. So the new thing we need to talk about is what this norm is. It's not, when we were talking about the function f being Lipschitz, we just used the absolute value of f of x minus y, f of y, so that was easy. When we talk about the gradient being Lipschitz, well, that was the difference between two vectors. So we just used our vector norm, Euclidean norm or some other vector norm. But now we need some norm that can measure the distance between matrices. And we're going to use here what's called the operator norm or the 2 norm. And as a brief aside, if you haven't seen this, if I have a matrix M that is symmetric, its operator norm is just equal to, well, in general, whether it's symmetric or not, it's equal to, it's the largest singular value of M. And if it's symmetric, this will equal the absolute value of the largest in absolute value eigenvalue. Again, I hope my notation here is clear. So it's not the most positive eigenvalue, but it's the eigenvalue, it's the absolute value of the eigenvalue that's farthest away from 0. So this measures the Lipschitzness of the Hessian. Okay, so if these properties are satisfied, and again, note that just by writing a Hessian, I'm implying that it's twice differentiable. Then there exist constants lambda, where 0 is less than lambda is less than little m, which is the strong convexity parameter, over twice capital L, which is the Lipschitzness of the Hessian, which is what we defined a second ago. And then gamma equals alpha times beta times lambda squared times little m over capital M squared, such that it doesn't really matter what they, I mean, there's a specific form, but the key is the following. Let's not get too hung up on exactly the definition of these constants, such that the following holds. If the gradient at a particular point is big, because we're smooth and strongly convex, you can't have a big gradient and be close to the optimal solution. Because of smoothness, if you have a big gradient, we know that we're far away from the optimal solution. So if this gradient, in other words, if we are not close to x star, note that we don't want to put this as a condition because we don't know where x star is. So if I tell you what x is, you can't just subtract it from x star and find out how far you are. But because of smoothness, knowing the gradient is big or small, because of smoothness and strong convexity, this gives us a proxy for how far away we are. We can turn this into bounds on how far away we are. So if the gradient is big, we are in phase 1. And we use damped Newton with what step size? Well, the step size that we get from backtracking line search. With backtracking line search. And if, on the other hand, this gradient, again, this is something we can check, is less than lambda, that means that we're in phase 2, the region of quadratic convergence where we can use undamped gradient. We are in phase 2 and can use step size equal to 1, in other words, undamped. And then in that case, we have quadratic convergence. And this is really the key promise of this theorem. So of everything to focus on, it is the fact that in phase 2, we have quadratic convergence that is as follows. At that point, xt plus 1 minus x star is less than or equal to the Lipschitz parameter of the Hessian divided by the strong convexity parameter times xt minus x star squared. This square, as we're going to see in the next slide, is the key and is what gives us quadratic convergence. There's one more detail here. So in the first part, if we are in phase 1 and we use damped Newton, I forgot to write the conclusion here, this means that at every step we will make constant progress at least, which means that after a finite number of steps, we're going to exit phase 1. So in other words, we're guaranteed that f of xt minus f of xt plus 1 is greater than gamma. So in other words, we're making at least progress gamma. Satisfies the following. xt plus 1 minus x star, my distance to optimal, is upper bounded by L over m. L is the Lipschitz constant of the Hessian, little m is our strong convexity parameter, times xt minus x star squared. So let's check what this means. Why does this imply such fast convergence here? Note that capital L could be much bigger than little m. We haven't mentioned anything about the relationship. So what saves us, and the whole key to quadratic convergence, is the square here. And the fact that xt minus x star is very small to begin with. Note that if that weren't the case, then this actually wouldn't tell me anything. If xt minus x star might be big, in particular if it's bigger than 1, then its square will be even bigger, and capital L could be very big as well. So this is why it's important that this result is a local result, and this is why we can move to phase 2. So let's actually plug in the upper bound and see what we get. So this is less than or equal to L over m, and now instead of xt minus x star, I'm just going to plug in the upper bound, little m over 2L. Little m over 2L, this whole thing squared. And doing this out, you'll see what's going to happen. I'll have 2 copies of m on top, 1 on the bottom, so this will leave me 1 copy of L on the top. I have 1 copy of L here, but I'm going to get an L squared on the bottom here, so that'll leave me with an L on the bottom. I have a 2 in the denominator, but that's squared, so I'm going to write I'm going to use one of those 2's there so I can keep this m over 2l factor, and then I get my 1/2 here. So first of all, we see that if xt minus x star satisfies this key condition, namely that it's less than m over 2l, then certainly xt plus 1 minus x star is also going to satisfy, because what we just showed is that it's less than half times m over 2l. Let's keep going. What is xt plus 2 minus x star? Well, it's going to be less than or equal to L over m times xt plus 1 minus x star squared. That's the promise. Plugging in this term on the left here, on the right, so plugging in this upper bound, I'll get in turn that this is upper bounded by, now let's see what's going to happen. The 1/2 is going to get squared. It'll be 1/2 to the 2. Then I'm also going to get another 1/2 the same way I did before. You can do out these calculations, and then I'll still preserve my m over 2l. So this will be less than 1/2 to the 3rd times m over 2l. Again, I'm writing it in this way to make it absolutely crystal clear that xt plus 2 will also satisfy the key condition. And keep going. This is just a matter of multiplying out simple little algebra. This is less than 2 over, L over little m of xt plus 2 minus x star squared. Squaring, I'm going to get 1/2 to the 6th, and I'm going to pick up another copy of half, just like we did before. This will be 1/2 to the 7th times m over 2l. Repeating, xt plus 4 minus x star will be less than or equal to 1/2 to the 7 times 2. That's 14, plus I'm going to pick up another half to the 15 times m over 2l, and you can see the general pattern here. So after k steps, xt plus k minus x star is going to be upper bounded by 1 over 2, and what's this formula here? 4 turns into 15, so that is just going to be 2 raised to the k minus 1 times this thing m over 2l, which is no longer important to us. So let's look at this convergence. We're converging like 1/2 to the 2 to the k, and that's why this is so fast. So let's again just quickly compare. Linear convergence looks like 1/2 to the t, and quadratic convergence looks like 1/2 to the 2 to the t. Again, the 1/2 and the 2, these are just constants. They're not that important here. The importance is recognizing how much faster linear convergence, quadratic convergence is compared to linear convergence. In the next lecture, we're going to move to the details of the proof of this phase 2 of quadratic convergence. We're going to stop here and pick it up then.